Hello dear viewers, this is your Math and Chem tutor. Today I'm presenting nuclear processes, a topic that was requested by one of the colleagues, so I saw it fit to come and discuss this topic here. Now, if you have any other topic you want me to discuss, please you feel free to send me a message in my inbox using the contacts that are running on the screen there. Now, basically, these nuclear processes are actually three of them: nuclear fission, nuclear fusion, and radioactivity. Radioactivity is always moving with half-life, so you can say radioactivity and half-life. Now, this area, when they are examining it, it actually makes up item 1, because item 1 comes from item 1 comes basically from 4 topics, that is medicine and drugs, then also food additives, detergents. These are actually products. These are called products. Then the 4th one is a process called the nuclear processes. Now, nuclear processes are divided into nuclear fission, fusion, and radioactivity. Now, there are 4 basic questions when they are examining this item here. So, the questions under this item 1, questions under item 1, they will always ask the learner to state the category. Then they will ask the learner to state the function or how it works, how the process works, how the product works, etc. So we are looking at the process. So how it works. Now, how it works is different from when they say state the application or the importance or actually the use. So when they say state the use is different from the function for if you are dealing with nuclear processes. So function, for example, if you are talking about nuclear fission, you can say nuclear fission occurs when a neutron is bombarded onto a heavy nuclei like uranium-235. So that's when you are describing how it works or the function. But when they say state the use, you will say nuclear fission is used in generation of electricity. So that's the difference. But this is not applicable to medicine, food additives. Now, medicine and food additives, they use how it works, the function, the application, importance is the same thing. It's the same thing. But for detergents and nuclear processes, when you are dealing with the function, is different from the use. I hope that's made clear. Now, the 3rd question they will ask the danger. And here the learner is also asked to provide an explanation, then finally mitigate. Then lastly, they will ask the learner to evaluate. Of course, evaluation is stating similarity and the difference. But most times, they will not set a direct question that evaluate or state the similarity and difference. They will set a question which is comparative in nature, such as, for example, they can say, guide the company on which process is better to use. The word better is a comparative term, so they can change the language and be careful when they are using comparativeness. So let's dive into splitting down these processes. Now we are starting with nuclear fission here. So fission means splitting. So nuclear fission is a splitting of the heavy nuclei, and majorly they use uranium-235. Of course, the other isotope of uranium-238 is used in something else. So uranium-235 and plutonium are commonly used to induce nuclear fission. Plutonium-239, as we shall see it later. So when the heavy nuclei splits, it splits into smaller nuclei such as barium and krypton. We can look at the equations here. So uranium bombarded with neutrons gives barium and krypton, which are of course smaller, with smaller atomic masses, then releasing more neutrons and energy. These more neutrons can induce a chain reaction. That's why nuclear fission is associated with further chain reactions, producing more newer elements and a lot of energy. So this process is the commonly one used in nuclear processes in most of the items, because it is the one responsible for high energy release, and it's possible in the nuclear reactors and in the atomic bomb. So it's possible on Earth here. But its friend nuclear fission, we shall see that it is commonly used in the stars and the sun to generate that lighting and heating. But its technology on Earth is actually very, very difficult to use, to come up with. So we have used an illustration here that a heavy nucleus of uranium is bombarded with these neutrons and ends up being unstable, because the particle numbers increase, the neutron number will have been added to this, so that now it splits down into this and that, releasing a lot of energy. So let's dive into nuclear fusion. Now, when we are dealing with nuclear fusion here, to fuse is to combine. So, two light nuclei, normally they use deuterium and tritium. These are what takes place in the sun and of course the stars, to be responsible for the heat from the sun and the stars. Of course, the technology on Earth has been actually very difficult. That's why we are saying not yet available in power plants. So it's difficult on Earth. That's why the item for last year, you named 2024, a learner who stated nuclear fusion was actually not possible to score that, because this process can't even release sufficient energy that is comparably higher than nuclear fusion. So when the lighter nuclei such as deuterium, this of course will stand for deuterium, then this is tritium, will combine to form this one, a helium nucleus, and releasing a lot of energy and some more neutron. So we can see it in the illustration here, that deuterium here will combine with tritium here. I think you can see these are deuterium 2 particles, then down in 3 particles, they will form, undergo fusion to form helium, and actually releasing some good amount of energy and more neutrons here. Let's dive into radioactivity. So radioactivity is actually decay of unstable atomic nuclei. It breaks down. To decay is to break down into new elements with the release of energy. So energy is released in form of radiations, and there are 3 types of radiations which come up as a result of nuclear, as a result of radioactivity. Now the energy from radioactivity is actually too little. That's why it is applicable on small scale processes, not on large scale production of electricity. So items having electricity and use sums of energy, radioactivity can't qualify as the category, because the energy release is actually too little. Now we can see this process that unstable nuclei actually undergo decay or breakdown to produce new elements with actually release of energy. We've not demonstrated here some key equations, but that's what happens in radioactivity. So let's dive into some similarities here in the processes. All the 3 processes are what we are looking at. So we are looking at a similarity between the 3 processes. So we are dealing with the similarity in nuclear fission, in fission, also fusion, and radioactivity. So how are they similar? All the 3 processes actually involve changes in the nucleus. So they are called nuclear processes, so they involve the atomic nuclei of the unstable atoms. So, and all of them release energy, but the energy varies in amounts. We say nuclear fission produces the most amount of energy, as we shall see the differences. Then nuclear fusion follows, then radioactivity. Then the resultant formation of new elements. Then lastly, they all need high technology, and of course they are used extensively in nuclear power, medicine and research. Let's look at differences. Now, these differences are actually applied in evaluation together with similarities. Now, if the item has fission and fusion, then you'll be dealing with fission and fusion in your differences and similarities. If the item has radioactivity and N of this, then you'll check for what we'll discuss there. So, the first difference is fission is splitting down, whereas fusion is actually joining, then radioactivity is decay. Then in terms of amount of energy, highest amount of energy, much higher than the lowest amount of energy. Then which particles are involved here? Here we use normally uranium-235 and plutonium. Whereas here the inducing atoms are deuterium and tritium. Here there are a number of elements which can undergo decay, so we are given a few here. So this occurs in nuclear reactors, nuclear fusion occurs in nuclear reactors, and of course atomic bombs. Then fission occurs in the stars. Then radioactivity occurs in natural occurring elements called radioisotopes. Then what are the byproducts? Nuclear fission produces what we call radioactive waste, so it's very, very dangerous. Then the waste for nuclear fission is actually not dangerous because little waste and producing helium, which is actually not harmful. Then radioactivity produces radiations and new elements. Of course, the radiations are very harmful. Here, alpha particle, beta and gamma rays. Then nuclear fission can be controlled. Of course, can be controlled. Then fusion occurs naturally in the stars, so it can't be controlled. Very difficult to control and not yet attained on Earth. Then radioactivity happens spontaneously. Of course, some radioactivity can be induced artificially, so controlled. Let's look at some uses here. Now, each of these processes has some uses, but of course when they state the use, they have combined uses. Of course, generally they have combined uses, except some fuses like atomic bombs, which are actually strict for nuclear fission. So this atomic bombs is for fission. Then one specific case is hydrogen is for fusion. But of course both of them generate electricity and generate a lot of heat for large scale use, generate electricity, heat for large scale use, and more others. Let's look at uses of radioactivity. Radioactivity has a number of uses because it has a number of radiations or particles. So it can be used in industrial uses, medical uses, archaeology, geology, etc. For example, in the industry, it can be used in tracing the flow of liquids in chemical plants. It can also be used to find out the thickness of materials like paper, also detecting wear and tear in machinery, also detecting some faults in welded joints here. So in medical uses can be used treatment of cancer, killing bacteria, then sterilization of medical instruments. So you can check the specific radiation which do this, like gamma rays sterilize medical instruments. Then of course radioactivity can also be used in archaeology to determine the age of decayed plants in a process called carbon dating. Also, geologists determine the age of rocks. So you can read further on that. Let's dive into one item here, the first item, to look at how we approach these items. During the Second World War, the cities of Hiroshima and Nagasaki in Japan were bombed using the most lethal weapon. Of course, it was an atomic bomb or nuclear bomb, which caused massive destruction as shown in the figure. So it did show the figure, but it was UNEB 2024. However, the energy that was used can be useful in the treatment of cancerous growth. So up now the impact of the bombing is still being felt. Identify the category. So basically, the only option was nuclear fission bomb or nuclear bomb. So nuclear fission bomb. Also possible answer, or atomic bomb. Atomic bomb also correct, or nuclear bomb here. Only one category is required. Nuclear fusion is not possible because the energy is too little. Also the conditions needs high temperature and pressure. Then that process has not been realized on Earth yet because the technology is still difficult. Suggest any other use of the form of energy that was used in the bomb. Of course, production of electricity. Here they are asking for the use. The use is different from the function. So you state one use of nuclear fission. Then explain the other danger. So there are so many dangers. The first danger has been mentioned in the item. Then this other danger we can state and explain, then mitigate it. Causes mutations by disorganizing arrangement of genes or chromosomes. That's an explanation. Then mitigation is by wearing or putting on lady coats or personal protective gear. So you realize that this item lacks the part of evaluation because it lacks the part of evaluation because it's only containing one type of nuclear process. So you can't evaluate when there is one type of nuclear process. So some items will not have the two nuclear processes. Let's dive into item 2. So this item 2, many countries have resorted to using nuclear power. So nuclear power is actually, as a result, can be generated by both nuclear fusion and nuclear fission. We saw that in the uses. But because the technology of nuclear fusion is still difficult, but it can be generated out of nuclear fusion. So both categories are present in the item. Now, first item says, state the categories. So we are going to choose only one category because they award only one category. But even if a learner states C2, he or she will only score one item. Then part B, which requires how the process works. So this is the same as saying state the function. But when they say state the use, you only state the use, not how it works. Then we shall also look at the danger, explain it, mitigate it. Then advise on the process which is better to use. Better to use is a comparative language. So this is actually evaluating. Evaluate. So let's look at the responses. So, under category, we state either fusion or fission because both processes can generate nuclear power. Now, when they say explain how the process works, you pick only one category, then discuss that. So, if you discuss fission, well, if you discuss fusion, well, only one category is required. So nuclear power is produced by nuclear fission. How does fission occur? Uranium-235 or a heavy nucleus is bombarded with a neutron. As we said earlier, you can write the equation, but of course only the explanation is enough. This makes it unstable, causes it to split down into lighter nuclei such as barium and krypton, but you might not go into the details, which releases energy and more neutrons. We saw that. The neutron formed causes more atoms of uranium-235 to split down. We say this can go into a chain reaction. This process continues in a chain reaction. This is chain reaction because of the more neutrons which can keep bombarding on more uranium atoms and more newer elements formed. So that's how nuclear fission works. Let's look at nuclear fission. In nuclear fission, we say the lighter nuclei such as helium basically is what they use in the fission, so it's better to mention them. Combine under high temperature and pressure, of course high temperature is the most important, to form heavier nuclei called helium and more neutrons with the release of energy. So that's how it works. Let's look at the next part of the item. Now when they ask you the danger, they only want one danger, explain, mitigate it. So causes cancer, how? Radiations cause uncontrolled cell division. That's how cancer comes about. Then mitigation, wearing lead cords. Let's look at the advice. The advice just state one similarity. Both release a lot of energy. Then the difference, fission produces more energy than fusion. So fission is better. So that's what you say. Fission would be the best choice. Let's look at item 2. Item 3 rather. Uganda is exploring nuclear power. Now you see, nuclear power will actually involve fission and fusion to address electricity shortages. Science students from Busitema visit a research facility in South Africa where they observe uranium-235, so this is nuclear fission. So the item has fixed us to nuclear fission. We see that, so we are going to limit ourselves here. Now, they learn that barium-141, this product of fission here, emits harmful radiation. So a support equation is here. So now this is radioactivity because there is beta decay, because this is a beta particle. Emission of radiations, this is of course radioactivity. So this is radioactivity. So there are two processes here in this item. Nuclear fission and radioactivity. They tasked the students with evaluating whether Uganda should adopt technology using uranium or barium. But of course, we are saying that radioactivity cannot produce sufficient energy, so we would opt for nuclear fission. But of course, we must compare this way, must evaluate in part D. Part A said the category of the nuclear processes in barium and uranium. So we've seen already in barium there is radioactivity or nuclear decay or radioactive decay, but in uranium there is nuclear fission rather. Explain how the processes uranium and barium occur. So we are going to explain fission and radioactivity in barium. The danger occurring in the smaller nuclei, so we are going to look at the danger of radioactivity. Okay, let's dive into the responses. Now we see that in uranium we saw there is nuclear fission, in barium there is radioactivity. Explain how the nuclear processes in uranium and barium occur. Of course, we are going to explain fission and explain fusion. When uranium-235, we've already talked about that, so go through that. Then for radioactivity, of course, the unstable nuclei undergoes spontaneous radioactive decay, emitting beta particles, which transforms into a new element. We've already seen the new element as lanthanum. This process occurs naturally and gradually. Let's dive into the next part. Part C, explain one danger associated with the process in barium. Of course, we saw that barium is releasing beta radiations which are ionizing in nature and damage living cells, causing health effects like cancer and radiation sickness. It is mitigated by wearing lead cords. Of course, we state the danger, explain, then mitigate. Let's look at the evaluation part. Guide the students about the choice of the process which is better to use. Of course, we are saying that the process which is better will be in uranium. Similarity and difference. Both uranium and barium undergo nuclear changes in the atomic nuclei. That's one of them. Oh, of course, they need one. Of course, in both they release energy, but the energy in uranium will be higher. So difference, uranium undergoes nuclear fission which is triggered by a neutron, while barium undergoes spontaneous radioactive decay which happens naturally without external influence. So that's one of the differences. Of course, the other difference would be say nuclear fission in uranium produces more energy than radioactivity. So nuclear fission is the best choice, is the choice which is better for students to choose from. Let's look at the next item. So in the last item here, let's see what it says. A chemical manufacturing plant recently decided to use strontium-90 in a power source of its remote monitoring devices. So not power source for electricity. This is just small scale devices for remote monitoring. Strontium-90 is a radioactive isotope that undergoes beta decay. The item has already guided on this is radioactivity directly. The company selected it because of its long half-life of 28, so they have also given us half-life. Then, after 84 years of operation, the company notices a significant drop in power output. So let's look at the tasks. Identify the category. Of course, we've already agreed that's radioactive decay, or you can call it radioactivity, or you can call it beta decay or nuclear decay, any of those. Then how does the decay work? Of course, there is just emission of radiations to form a more stable element. Of course, here we are looking at generating some electric power for remote monitoring devices. So we add something here. Strontium-90 undergoes beta decay, releasing high energy beta particles that generate heat. This heat is converted into electricity using thermoelectric generators. So this radioactivity process is actually not applicable to nuclear reactors, but some small equipment like thermoelectric generators for low power generations. So calculate the amount of strontium-90, this is number 2, calculate the remaining amount of strontium-90 after 84 years. So we are going to use this expression, this is the equation, or you can use the table. So we want N, the amount remaining. So we don't have the initial, you can call the initial N naught. Then our total time is 84, our half-life is 28 from the item. So this is half-life. Half-life, then this is total time. Total time, then N is the amount left. Amount left, then N naught is the original amount. So we are calling original amount as N naught. So by putting in here 84 out of 28, that gives us 3. So it will be a half to power 3 giving us 1 out of 8. So we can express in terms of percentage you can say the amount left is an eighth of original. Or we can express in terms of percentage and say amount left, we shall be 100, representing N naught times an eighth. This is 12.5%. So this N naught can be replaced by 100 if you want it in percentage. So you can also use the table. Let's look at the next part. Discuss the dangers associated with the long-term use. Of course, this is radioactivity. The radiations can cause mutations, which is as a result of disorganized arrangement of chromosomes mitigated by wearing red coats. Here we have not evaluated because it's only fixed on radioactivity. So where the item has only one process, you don't evaluate. Thank you.